The reactions of alkynes are very much similar to the reactions of alkenes. So the first one is the addition of HX. We've considered this reaction in alkenes. But the difference is that with triple bonds, you have to add it twice. And you have the option of just adding it just once, or you have the option of adding it in excess. So let's move step by step. So if you start with an alkyne, and our alkyne here is a di-substituted alkyne. So whenever you have a di-substituted alkyne, always check the carbons of the triple bond and see which carbon is closer to the less carbons. That will be the less substituted carbon. So this carbon is connected to a CH3. This carbon is connected to a carbon in the carbon. So this one is going to be the less substituted carbon, and this one is going to be the most substituted carbon. So this is going to be the less, and this is going to be the most. Now we know that HX is going to add according to Markov-Nikov. And when it adds according to Markov-Nikov, in this case, I'm going to end up getting a carbocation. So Markov-Nikov says that hydrogen is always added to the less substituted carbon. So hydrogen here is going to add to the less substituted carbon, and the halogen is going to add to the most substituted carbon. The halogen in this case can be any one of those halogens. In rare cases, we're going to use the fluorine because fluorine is a very bad leaving group. So the reaction is going to start by the triple bond being our nucleophile. And that triple bond is going to open up and pick the hydrogen. So it's going to pick up the partial positive hydrogen. Every time you make a bond, you break a bond. So you're going to end up getting the hydrogen on the less substituted carbon and the positive charge on the most substituted carbon. My intermediate here is going to be my carbocation that is on the alkene, which we call it a vinylic carbocation. I'm not done with my first step because now X is going to be in the solution. So now X is going to come and attack that plus a charge. When it attacks that plus a charge, now you have a possibility of formation of stereoisomers in there. Don't forget, since the positive charge is going to be planar, then the X has two ways to attack. The X can attack either from the top or it's going to come and attack from the bottom. So I'm going to end up forming the E and the Z stereoisomer. Now here I'm not showing the E and the Z, and the reason why I'm not showing them because I am continuing the reaction. This is why it really doesn't matter because at the end you're going to form the alkane. But if you are using just one equivalence of HX, you have to show the E and the Z. Let's go ahead and show the E and the Z for now for this one. So this over here can be either E or Z. So for the Z, the X is going to be on the same side of the CH3, and that is going to be the Z isomer, plus the E isomer is when the X is up and the CH3 and the ethyl group is on the same side, and this is going to be the E isomer in there. The reason why this one is a Z because the X has a higher priority than the ethyl group, and the CH3 has a higher priority than the hydrogen. And both the X and the CH3 are on the same side, so this is going to be Z. Here, X has a higher priority than the ethyl, and the CH3 has a higher priority than the hydrogen. The X and the CH3 are opposite to each other, so this is why this is an E isomer. So again, you show the alkene isomers whenever you are using just the one equivalence of the HX. If you're using two equivalents, no need, because anyways, you are going to form the alkene at the end. So now for the second equivalence, you're still going to follow the Markov-Nikov. And hydrogen will still add to the less substituted carbon, and the halogen is going to add to the most substituted carbon. So you're going to start by, this is a simple alkene now reaction. Double bond is going to open, take the hydrogen, halogen is going to leave. The hydrogen is going to add to the less substituted carbon, and the adjacent carbon will carry the plus charge. X will be in the solution, and that will attack. In this case, I'm not forming a chiral center because the X's are the same. So right now it doesn't matter. It's just going to attack, and I'm going to end up forming two halogens on the same carbon. This is called a gymnal dihalide. Okay. Let's have an example over here. So if you have your triple bond with the two HBr, the hydrogens are going to add to the less substituted carbon. So this is where your triple bond is. Let's highlight that. So this is where your triple bond is. And what I am doing here is that I am adding my hydrogens to the less substituted carbon, and I am adding my halogens to the most substituted carbon. This carbon is the less substituted carbon. This carbon is the most substituted carbon. The mechanism you are responsible for. So you highlight your triple bond. This is where your addition is. Know which carbon is the most substituted and which carbon is the least substituted. So this one is going to be the least substituted, and this one is going to be the most. So hydrogen always adds to the least substituted carbon. So hydrogen is going to come and add to these, and it's going to add it twice because I am using two equivalents of the HBr. So it's going to come and add it twice. And on the adjacent carbon, I have my bromine. So I would know where is my position of the triple bond. My position of the triple bond is between those two carbons because I added two HBRs. Triple bonds can do anti-Markovnikov reaction, but this time we are using just HBr. As we did with the double bonds, HBr only works with anti-Markovnikov. HCl and HI, we try to avoid those with anti-Markovnikov. They don't work. And we're going to still add either one equivalence or two equivalents, but the difference here is that we're going to ignore stereochemistry. So here we're going to ignore stereochemistry. If you're adding one equivalence, then according to anti-Markovnikov, hydrogen is going to add to the most substituted carbon. So this carbon over here is going to be the most substituted, and this carbon over here is going to be the least substituted. So hydrogen is going to add to the most substituted carbon. So hydrogen is going to come and add over here. Bromine is going to come and add over there. If you're adding one equivalence, then you can stop here. Now you can continue if you're adding HBr again. Two equivalents of HBr, continue, and then hydrogen again will be added to the most substituted. So hydrogen will be added on this carbon again, and the bromine is going to be added to the least substituted. So again, you're going to end up getting your gymnal dihalide. Consider the halogenation of alkenes before. The halogenation of the alkynes is very much similar in terms of mechanism. The only difference is that I am using the halogen twice. The halogen can be either a chlorine or a bromine. So we're going to start by the triple bond opening up and picking up the halogen. The lone pairs of the halogen is going to close exactly as we did with the alkene. But the difference here is that the pi bond or the triple bond has two pi bonds. So if I am opening up one pi bond to make the cyclic chlorinium ion, the other pi bond is going to stay there. This is the only difference here. So I am making the cyclic chlorinium ion, but this is going to be an alkene. It's not going to be an alkane. And as we said before, since chlorine shares a plus charge, every single carbon in the cycle will be also partial positive, just to make the structure more stable and not focus the charge on just one element of the cycle. It's going to be a charge distribution. So this is going to make this carbon more partial positive like carbon because it is a more substituted carbon. So the chlorine now, which is in the solution, and the chlorine in the solution came from the chlorine that left over here. So this chlorine now is going to come and attack this carbon. It's going to attack it from the opposite side of the cycle. So always, you are going to end up getting your E intermediate. So this is going to be the E isomer. This is always the case with this reaction. You're never going to get the Z. You're going to get the E isomer, where you're going to end up having your two halogens. They are on opposite sides. Now you're going to stop this reaction here if you are using just 1 mole of the chlorine, showing the E isomer. If you are using a second mole of the chlorine, then this is going to be exactly the same as the addition reaction of halogens to the alkene. So now the double bond is going to open up, pick the chlorine, and then the cycle is going to close. We're again going to form the cyclic chlorinium ion. And again, the plus charge will be distributed across every carbon in the cycle. And the chlorine is going to come and attack the most partial positive like carbon, which is this carbon over here, opens the bond. But now I don't care because I am having a single bond, and you know that I can have a free rotation around the carbon single bond carbon, and I don't even need to consider any stereochemistry, especially because all the chlorines are the same as well. So the chlorine is going to come and attack, open the bond. So now on each one of these carbons in here, I ended up adding 2 chlorines. So it's going to be a 4 chlorine total. So I know now if I go backwards, this was the position of the triple bond. There are different solvents that we use for these reactions. We can use carbon tetrachloride solvent, and these solvents, as we said before, they are only to make the reagent and the reactant being miscible with each other. So you're not going to see them in the product whatsoever. So this is a solvent in here that we can use. Another solvent that we can use is acetic acid with lithium bromide. This is just a solvent. So whenever you see that, just go ahead and ignore. The only role for this one is to make, again, the bromine and the triple bond miscible with each other. Just ignore. So here in this reaction, I am using 1 equivalence of the bromine. So if you're using 1 equivalence of the bromine, please go ahead and show the stereochemistry of the reaction. So let's draw the mechanism of the reaction because you are responsible for the mechanism in there. So it's going to be partial positive, it's going to be partial negative. So the triple bond is going to open up, pick up a bromine, and the lone pairs are going to close to form the cyclic brominium ion. So you're going to form your cyclic brominium ion. Don't forget your double bond in there. And then you have your 2 CH3s. Now, since the addition is going to be a trans addition, go ahead and do your 2 CH3s in there, being opposite with respect to each other. Anyways, they will be opposite with respect to each other once the Br minus starts to attack. So now you're going to have a Br minus in the solution, and that Br minus is going to attack from the opposite side of the cyclic brominium ion. We've said that each one of these carbons is going to share a partial positive charge, but because they have the same degree of substitution in here, it doesn't matter where the Br is going to come. So I'm just gonna allow the Br to come and attack this carbon. So the bromine over here is gonna come and attack from the opposite side of the leaving group. So I'm gonna end up getting my trans product in this case. So the bromine now is going to be trans. Those 2 bromines are going to be trans, and the CH3s, they're going to force the CH3s to be trans. So let's say if you forgot to put the CH3s trans in here, the attack of the bromine should remind you that this is going to be trans, so the CH3s have to be trans as well. Now, I can go ahead and stop the reaction here if I'm using 1 equivalence. If I want to go ahead and use another equivalence of the bromine, then in this case, I'm going to form again the cyclic brominium ion. So here I'm using again the second equivalence. Again, mechanism you are responsible for. So the double bond is going to open up, pick up the bromine, and the lone pairs are going to come in the close. So you're going to form, I'm going to write the cyclic brominium ion over here. So you're going to have your bromine over here, and then you have a bromine here, a CH3, and another bromine here, and another CH3. Now, each one of these again is partial positive, but it doesn't matter because both they are the same. They have the same degree of substitution. So now let's put it this way. So now we're going to go ahead and add the Br minus, which is in the solution. So this here is going to be my Br minus is going to be in the solution. So that Br minus is going to come and attack this carbon, open the bond, and I'm going to end up forming my tetra-bromo product. This is an example. So every time you are using 1 mole of the halogen, make sure that you are forming the E product. If you're using 2 moles of the halogen, you don't have to show the intermediate. Just go ahead and show the final product in there where you're forming the tetra-bromo product.